today is our last class of our renal physiology, and especially the acid-base balance, as I have written here, the concluding part of our discussion on acid-base balance. Now, for last two classes, I briefly described the mechanism of acid-base regulation, and I mentioned that there is a major pH threat, 10,000 plus 50 to 100, that much millimole per day. So that is the pH threat. That is the pH threat. How it is there, what it is there. How we have described everything. So this is the pH threat per day. And I also mentioned that by respiratory regulation, there is around, say, 5,800 millimole is handled. By renal regulation, around 4,300 plus is handled by renal regulation, or within renal regulation by bicarbonate recovery. By bicarbonate recovery, this much amount of H plus ion is handled, and by new bicarbonate. So this is the bicarbonate recovery, and by new bicarbonate, around 50 to 100 millimole of hydrogen ion is handled per day. So this we have described. This I have described in my last class. What we mean by recovery of filtered bicarbonate, reclamation of filtered bicarbonate, and how much it can take place, as I have mentioned here. And when it's even in excess of that, some extra hydrogen ion is secreted with the tubular lumen, what is the fate of that hydrogen ion? And for each molecule of hydrogen ion secretion, there is a returning of HCO3 in the circulation, but in the tubular lumen there is no remaining bicarbonate, so H plus ion remains free, otherwise free, which is handled by two buffer mechanism. One is the phosphate buffer, another is by ammonia buffer. So how they are handling that free hydrogen ion, that also I described in my last class. So based upon that, today I will finish up the acid-base balance. Now few things are left, and few terminologies which you need to know. Certain terminologies which you need to know. First of all, that hydrogen ion which is secreted as a result of generation of new bicarbonate is being handled by, as I have mentioned just now, is being handled by phosphate buffer and ammonia buffer. Now this phosphate buffer, while buffering the hydrogen ion, is converted into H2PO4, phosphoric acid, and NH3 is converted into NH4+. Now, out of these two, so these are the two ways by which the excess H plus ion, which is secreted in response to generation of new bicarbonate, is generated. And out of these two, this H2PO4, this one is specifically present as a titrable acid in the urine, which we can titrate by using standard titration method, as we did in our high school chemistry lab. So this part, H2PO4, is a titrable acidity. So this H2PO4 is also known as titrable acidity, whereas this ammonium part is not titrable. Why it is not titrable? There are detailed explanation with respect to physical chemistry, which we can do if you are interested. So these H2PO4 or product in the urine is responsible for titrable acidity. So this is number 1. Number 2. So this is number 1. Number 2. If we try to show this titrable acidity, this amount of titrable acidity and the amount of ammonium present, titrable acidity and amount of ammonium present, the combination of these two, that means titrable acidity due to the presence of phosphoric acid and presence of ammonium ion, these two indicating the amount of new bicarbonate generated. So these two are indicating that amount of H plus ion which is buffered, which was generated as a result of or as a consequence of generation of new bicarbonate which is entering into the circulation. So accordingly, this combination of these two is indicating the net amount of new bicarbonate which is generated. So titrable acidity plus NH4 contained in the urine is said to be the net bicarbonate, new bicarbonate generated. Net amount of new bicarbonate generated. So these are the two things. These are the two things which we can remember. Now, why I am telling all this? I am telling all this because these things are net bicarbonate generation, titrable acidity, then a non-titrable portion of non-titrable fraction of ammonium present in the urine. All these terminologies are used very frequently when we discuss in detail about the acid-base imbalance. When all these things are discussed, that will be taken into consideration. So in future, when you will learn in detail of acid-base imbalance, all these things will come into play. So that's why I am just mentioning these terminologies. So this is about that. Now next point, next important thing I like to discuss is the regulation. Regulation of H plus ion secretion. So H plus ion which was secreting, about which I discussed in detail, H plus ion secretion, or more specifically bicarbonate derived H plus ion secretion. Bicarbonate derived H plus ion secretion, whether it is a recovery of bicarbonate or generation of new bicarbonate, whatever it is, ultimately H plus ion is secreted in the tubular lumen. So let us see how this H plus ion secretion is regulated, or what are the important factors which regulate this H plus ion secretion. Now, the most important factor which is responsible or which is regulating the H plus ion secretion across the tubular lumen is intracellular pH. So this is the most important factor. Intracellular pH or ICPH, this is the most important factor which is regulating the hydrogen ion secretion across the renal tubular epithelium. Now, so what is intracellular pH? Intracellular pH is the pH of the intracellular fluid. pH of the intracellular fluid, that is called ICPH. So this is the by far the most important determinant. Now this, as the intracellular pH is going down, the hydrogen ion secretion across the tubular epithelium will increase. As the intracellular pH is going up, the hydrogen ion secretion across the tubular epithelial cell decreases. So in case of intracellular increase as acidosis or increase hydrogen ion concentration inside the cell, H plus ion secretion will increase, or decrease H plus ion concentration inside the cell in the intracellular fluid will lead to decrease in the H plus ion secretion through the tubular lumen. So this is the very important regulatory factor. Now this intracellular pH is again dependent upon two important factors. One is the pH of the arterial blood, pH of the arterial blood, and number 2 is the potassium ion concentration in the plasma. So these are the two factors which will rather determine the intracellular pH. So it is easy to understand that whenever pH of arterial pH is low or high, that will accordingly reflected in the intracellular pH. So this is one thing. Now this is easy to understand. This is not very difficult to understand. But how potassium ion concentration in the plasma, how the potassium ion concentration in the plasma is affecting the intracellular pH, that you need to understand a bit in a better way. Now you see, we all know that, say it is a cell, inside the cell the potassium concentration is high, outside the cell, so intracellularly potassium concentration is high, outside the cell potassium concentration is low, and also there are some impermeant anions are present inside the cell that we all know, mainly the proteins, inorganic phosphates, etc. Creatinine, phosphate, ATP, etc. So some impermeant anions are present inside the cell, and potassium concentration in the intracellular fluid is very high, and potassium concentration in the extracellular fluid, or say here extracellular fluid is quite low. It is a lumen, let us think in that way. Extracellular fluid is quite low. Now also inside the fluid there are various other ions. Now for any reason whatsoever, if the extracellular fluid potassium concentration is reduced, due to any reason whatsoever, if the extracellular fluid potassium concentration is reduced, what is known as hypokalemia, so the extracellular potassium gradient will increase. So potassium will tend to move out of the cell. And we also know the cell membrane are highly permeable to potassium, so potassium will tend to move out of the cell. Now in order to maintain the intracellular electrical neutrality, due to there is a presence of impermeant anions inside the cell, in order to maintain the intracellular electrical neutrality, what will happen? There is an operation of an antipode. There is an operation of an antipode known as potassium hydrogen antipode. So whenever there is hypokalemia, there will be greater tendency of potassium loss out of the cell. Now in order to maintain the intracellular electrical neutrality, especially due to presence of lot of intracellular impermeant anions, hydrogen ion will get in, and as the hydrogen ion will get inside the cell, the intracellular pH will fall, and when intracellular pH will fall, that will affect the hydrogen ion secretion. So this is how the potassium ion concentration in the plasma, in the extracellular fluid is affecting the intracellular pH. So in case of hypokalemia, hydrogen ion will tend to enter inside the cell, leading to reduction of the intracellular pH. So in case of hypokalemia, what happens? Although the intracellular pH is reduced, but the pH of the plasma becomes a bit alkaline, because there is movement of hydrogen ion out of the plasma into the cell. So in case of hypokalemia, although the intracellular pH will increase, leading to increased H+ ion concentration, but the pH of the plasma will be slightly alkalinic. Or opposite is true in case of hyperkalemia. So when there is hyperkalemia, the movement of the potassium out of the cell will be less. So entry of the hydrogen ion inside the cell will be less. So pH will not drop that much, and plasma pH will remain a bit acidotic. So this is how the plasma potassium concentration is affecting the intracellular pH, and in other words is also affecting the H+ ion secretion from the renal tubular epithelium. So this is about some of the important general regulatory issue. General regulatory issue of H plus ion secretion through the renal tubular epithelial cell. Now there is another very important issue. Another very important issue. We all know when we discuss the H plus ion secretion along the tubular epithelium, I told you that in the proximal tubule portion, the hydrogen ion secretion is done via NHE3, sodium hydrogen exchanger, or it can be written as sodium hydrogen antipode. So in the proximal tubule, the hydrogen ion secretion is done by sodium hydrogen antipode. But in the distal nephron, what we found that in the distal nephron, the hydrogen ion secretion is mainly H plus ion secretion is mainly active in nature. Not coupled with any other ion. It is mainly active hydrogen ion extrusion especially in the distal nephron. That we have told you in my last class. Now, point which I like to make at this juncture is that although we are saying that in the distal nephron, H plus ion secretion is independently active in nature and thereby independent, not dependent on any other ionic movement. But there is a rider, or there is a precondition, or there are certain conditions. What are they? That is known as an issue which I have touched much earlier, in my earlier days of renal classes, that is trans-epithelial potential difference. Can you remember? Trans-epithelial potential difference. What is trans-epithelial potential difference? It is not transmembrane potential difference. Transmembrane potential difference is usual resting membrane potential. Trans-epithelial potential difference, if you remember, in my earlier class I told you, it is a lumen, inside lumen and outside lumen. Potential difference between inside lumen and outside lumen. Suppose an electrode is placed inside the lumen of the tubule and another electrode is placed outside the lumen of the tubule, and if they are connected with the sensitive galvanometer, that will give you a reading, and that is known as trans-epithelial potential difference. Now it is found this trans-epithelial potential difference which becomes substantial. If you remember my earlier figures, please refer to my earlier figures. This trans-epithelial potential difference becomes substantially high in the distal nephron. It is substantially high in the distal nephron. And as more and more sodium is delivered, if more and more sodium is delivered in the distal nephron, more and more sodium will be reabsorbed out of the distal nephron. Because again there is another factor I told you earlier, that is load dependent sodium reabsorption. So two important things I like to recall. One is trans-epithelial potential difference, another is load dependent sodium reabsorption. So two important things you please recall. One is trans-epithelial potential difference, another is load dependent sodium reabsorption. So as more and more sodium is delivered in the distal nephron, more and more sodium will be reabsorbed out of the tubular lumen, and accordingly more and more lumen negative trans-epithelial potential difference will be developed. Greater amount of trans-epithelial potential difference with lumen negativity will be developed as more and more sodium is delivered in the distal nephron. And that transluminal negativity will help hydrogen ion secretion. Will enormously help this active hydrogen ion secretion in the distal nephron. So this is another very important regulatory point in the H plus ion secretion, especially in the distal nephron. That is, that although hydrogen ion secretion in the distal nephron is by and large active in nature, not essentially dependent on any other ionic transport, but somehow sodium reabsorption indirectly affect, modulate the hydrogen ion secretion or active hydrogen ion secretion in the distal nephron. How? By developing a lumen negative transepithelial potential difference due to load dependent reabsorption of sodium. So, if you remember this, when in a situation when more and more sodium is delivered in the distal nephron, if it happens in a situation where more and more sodium load is delivered to the distal nephron, the hydrogen ion secretion will be more and more, and that will definitely affect the body's acid-base homeostasis or body's acid-base balance. So this is some of the outstanding issues which I did not touch or which I could not cover in my last class. Now next, and finally, I like to describe some aspect of the acid-base imbalance. Acid-base imbalance. So let us introduce yourself in the discussion of acid-base imbalance. Now, truly speaking, this acid-base imbalance issue is a very big issue. Acid-base imbalance issue is a very big issue, and it takes substantial time. I am not intending to enter into the details of it. Today, I will just introduce into the topic, and it will take substantial years of our life to understand the acid-base imbalance in a proper manner. So, today we shall just start. I will just introduce the topic, and it is the onus on you to become the master of acid-base imbalance. So, what is acid-base imbalance? So, acid-base imbalance means when our body, when our physiological system could not completely tackle the pH threat. Due to any reason, due to any disease state, due to any reason, whatever reason, due to any disease state or whatever it is, when our body or our altered physiological system, when it is in a state of pathological state, failed to tackle, failed to compensate adequately the pH threat on our body, pH threat on our system, then it will lead to development of acid-base imbalance. Now, to understand acid-base imbalance, I will take the help of a very simplified system, a very simplified way. I will take the help of the Anderson-Hasselbalch equation. So, what is acidosis? When the body fluid pH is low, that is known as acidosis. So, what is acidosis? Acidosis. So, when body pH is low, that is acidosis. What is alkalosis? When body pH is high. What is normal body pH? 7.4. So, when it is more than 7.42, it is alkalosis. When it is less than 7.38, it is acidosis. Because pH scale is a log scale, so extremely sensitive scale. Very, very sensitive. So, when it is more than 7.42, it is alkalosis. When it is less than 7.38, it is acidosis. So, how this acidosis and alkalosis can develop? As I have told you, I will take the help of Henderson-Hasselbalch equation. So, let us write the Henderson-Hasselbalch equation or the modified Henderson-Hasselbalch equation. So what is the modified Henderson-Hasselbalch equation? I told you that the most important, physiologically most important buffer is the bicarbonate buffer. So I will write the Henderson-Hasselbalch equation with respect to the bicarbonate buffer. So if I write like that, pH is equal to pKa plus log of HCO3 minus, that means the conjugate base, and PO2. So that was the modified Henderson-Hasselbalch equation. Modified Henderson-Hasselbalch equation with respect to the bicarbonate buffer, and this equation we have described adequately. So this is that. Now, when an acidosis can develop. So acidosis means pH is low. Now, how the pH can be low? It is very simple. pH can be low. When the pH is low, pH can be low by two possible mechanisms. Either by increasing PO2 or decreasing plasma bicarbonate. So this is the plasma bicarbonate concentration, and this is the PCO. Excuse me. So PCO. So this is the modified Henderson-Hasselbalch equation. So pH can be reduced or acidosis can be developed due to two possible situations, either increase in PCO2 or decrease in plasma concentration of bicarbonate. Or in other words, if the pH is increased, when pH is increased, it can be either due to two possible reasons, either increase in plasma bicarbonate concentration or decrease in PCO2. So it is simple. So if we follow the Henderson-Hasselbalch equation or modified Henderson-Hasselbalch equation, we can easily define what is known as acidosis and what is known as alkalosis. Acidosis means it is either due to increase in PCO2 or decrease in plasma bicarbonate, and alkalosis means either it is due to decrease in PCO2 and increase in plasma bicarbonate. Now let us see when these four situations happens. Now so we can write like that acidosis may be either due to rise in PCO2 or fall in HCO3 concentration in the plasma. Or alkalosis may be fall in the PCO2 or rise in the HCO3 concentration. So that this can be easily reduced. Now, when acidosis is due to this, it is known as respiratory acidosis. That is acidosis due to respiratory cause. When alkalosis is due to this, it is known as respiratory alkalosis. Or in other words, if the acidosis is due to this reduction in the plasma bicarbonate concentration, it is known as metabolic acidosis. And if the alkalosis is due to the rise in the bicarbonate ion concentration, then it is known as metabolic acidosis. So if the acidosis or alkalosis is due to change in the PCO2, then it is known as respiratory acidosis or alkalosis. Or acidosis or alkalosis if it is due to the change in the plasma concentration of bicarbonate, either rise or fall, then it is known as metabolic acidosis or alkalosis. So it is very simple. Now let us see what may be the possible cause of this. So if we remember this Henderson-Hasselbalch equation, then everything becomes very, very easy. Everything becomes very, very easy. So I write again, because that will require pH is equal to pKa plus log of HCO3 minus PQ. So what is the reason for respiratory acidosis? So respiratory acidosis means rise in PCO2. How a PCO2 can be raised? This PCO2 can be raised. The common cause is hypoventilation. If the ventilation is reduced. If you remember my last class, when I described the respiratory regulation of acid-base balance, I told you that alveolar ventilation is inversely proportional to PCO2. So if PCO2 increases or decreases, alveolar ventilation decreases or increases. So if the alveolar ventilation is reduced, PCO2 will rise. Or we can write like that also, because that should be the we can write like that also. So when alveolar ventilation is reduced, the PCO2 will rise. Here it is the independent variable and this becomes the dependent variable. Y is equal to fx. So this is the independent variable and this becomes the dependent variable. So in case of hypoventilation, it is a rise in PCO2, and when there is a rise in PCO2, there will be acidosis, and that acidosis is known as respiratory acidosis. So that is the reason for respiratory acidosis, when there is accumulation of CO2 in our body, either due to hypoventilation or due to any respiratory reason. When substantial amount of our respiratory tract is damaged, then there will be effectively accumulation of CO2 in our body, what is known as hypercapnia, and due to hypercapnia, it will lead to respiratory acidosis. So this is very easy to understand. What about respiratory alkalosis? Respiratory alkalosis. So respiratory alkalosis means when PCO2 is low. When PCO2 can be low? PCO2 can be low when there is hyperventilation. That is when we are ventilating more and more, large amount of CO2 will be washed out. So when large amount of CO2 is washed out, PCO2 will be reduced. When PCO2 is reduced, the pH will rise, and that is known as respiratory alkalosis. When we can see it, we can see in case of neurotic anxiety state neurosis, when there is increased rate and depth of respiration. Increased rate and depth of respiration continuously, consistently there is increase in the rate and depth of respiration, then it can lead to development of fall in the PCO2, leading to rise in the pH, and that is respiratory alkalosis. Now let us see what is metabolic. What is metabolic acidosis? So what is metabolic? When there will be metabolic acidosis, that means pH is low due to this. So when pH will be low due to this, when the plasma bicarbonate concentration is reduced. When the plasma bicarbonate concentration is reduced, that is known as metabolic acidosis. And when the plasma bicarbonate concentration is increased, that is known as metabolic alkalosis. So when we shall get metabolic acidosis? We shall get metabolic acidosis in that situation when plasma bicarbonate level is reduced. When the plasma bicarbonate level will be reduced? Plasma bicarbonate level will be reduced in that situation when the returning or recovery or generation of new bicarbonate, recovery of filtered bicarbonate or reclamation of filtered bicarbonate or generation of new bicarbonate is not adequate to tackle the acidosis or tackle the pH threat. And in that situation, plasma bicarbonate level will be low. I told you that whenever some acid threat is produced in our body, the first line of defense is buffer. The first line of defense is buffer. Say bicarbonate buffer, it is the first line of defense. And later, by renal method, by kidney method, that bicarbonate is recovered from the filtered fluid. Also, some extra new bicarbonate is generated. When this recovery and generation of new bicarbonate is fall short of the bicarbonate buffer spent during buffering as a first line of defense, then the plasma bicarbonate level will be reduced and leading to generation of metabolic acidosis. One example, say diabetic ketoacidosis. Diabetic ketoacidosis, decay. When there is a uncontrolled diabetes, there will be metabolism of lipid in absence of adequate amount of glucose. Glucose is not entering into the cell, leading to genesis of various kinds of acids, ketone bodies, acetoacetic acid, beta hydroxybutyric acid, etc. Or in case of lactic acidosis. So whenever there is, or in case of shock, suppose somebody is suffering from hypovolemic shock or hemorrhagic shock, as a part and parcel of hemorrhagic shock, some acids, lactic acids and other kind of acids are produced. All these things will lead to metabolic acidosis by depletion of bicarbonate store. So plasma bicarbonate level will be reduced, and these patients are known as metabolic acidosis. And finally, what is metabolic alkalosis? Metabolic alkalosis means pH is increased due to rise in plasma bicarbonate level. When it can happen? When plasma bicarbonate level can be raised? Plasma bicarbonate can be raised in a situation, you can understand, when we are doing excessive vomiting. Suppose somebody is vomiting, leading to loss of acid-rich fluid, loss of large quantity of acid-rich fluid through vomitus, or somebody is undergoing nasopharyngeal suction. A Ryle's tube, a tube is inserted into the stomach and large amount of stomach content is sucked out due to any reason whatsoever, for any requirement whatsoever. So when there is a vomiting, when there is a large amount of nasopharyngeal suction or stomach suction, all these things will lead to excess loss of acid-rich fluid, and that will in turn lead to rise in the plasma level of bicarbonate, and which will lead to metabolic alkalosis. So what will happen? What will happen in respiratory? So if we write one by one, if we try to summarize one by one, so if this is the if these are the three factors, in case of respiratory acidosis, the pH will fall, PCO2 will rise, and bicarbonate level will remain more or less normal. In case of alkalosis, respiratory alkalosis, pH will rise, PCO2 will fall, and plasma bicarbonate will remain more or less unaltered, not much altered. Whereas in case of metabolic acidosis, the pH will fall, PCO2 remain more or less normal, and HCO3 concentration in the plasma will fall. Whereas in case of metabolic alkalosis, the pH will rise, PCO2 will remain more or less normal, and bicarbonate ion concentration in the plasma will rise. So just by measuring all these parameters, we can stamp a patient whether he or she is suffering from respiratory acidosis or respiratory alkalosis or metabolic acidosis or metabolic alkalosis. You need not memorize anything. Just take hold of this Henderson-Hasselbalch equation. Modified Henderson-Hasselbalch equation with respect to bicarbonate buffer and just apply your common sense. You will get the answer. But obviously things are not that simple. Things are not that simple. Things are much more complicated. Most of the time we get a mixed type of acid-base imbalance. Mixed type. Respiratory acidosis along with metabolic alkalosis. Respiratory acidosis along with metabolic alkalosis. Somebody having a hypoventilation problem, lung problem leading to respiratory acidosis, and also large amount of vomitus, metabolic alkalosis. So pH level is not much changed. Then it is difficult. So there are a lot of difficulties also, but this is the simple most skill by which we can understand the elementary level of acid-base imbalance. So this is more or less all about the what I intend to tell you about this acid-base balance. Most oversimplified manner, the most simple manner or most oversimplified manner. Things are not that simple. Things are quite complicated. But for the beginning, it is enough. Students, you will go through these notes, consult your books, discuss with your friends, take your own note, generate your own innovative question, and then get to me. Send me question, your queries, your doubts, or directly call me, and we shall have discussion. I don't know whether we can conduct the Zoom class, interactive class, how long we can conduct, but at least we can answer your question in WhatsApp, in email, or through telephonic conversation. So this is more or less all about the acid-base balance. Only one thing I left, which I intend to present in the form of a PowerPoint, that is a discussion on diuretics. Diuretics is a group of drugs which are utilized to modify the urine volume. But I thought that with the help of understanding of diuretics, with the help of teaching diuretics, I will summarize whole of the tubular function. So that a small PowerPoint presentation I will be preparing and I will send to you, and with that we shall somehow finish the renal system. Only one thing I intentionally did not touch, that is the phenomenon of micturition, how urination is done. Urination is done, how urine is formed and urination is done. So how urine is formed we are covered, but how urination, the physical process of urination is done, that I have not touched. You please go through the books. They are not very difficult. They are easy to understand. The only difficulty is something related with neurogenic bladder or neurophysiology of bladder, which is difficult. But that will be taken after the teaching of nervous system is over. After Dr. Kumar will finish the nervous system, then we shall take a class or a half a class to discuss that part. That means neurophysiology of bladder. So that is a bit difficult to understand. Otherwise, whole of micturition is not very difficult to understand. So you go through the micturition, you set your question, you go through the whole subject, all the lectures what I have delivered, including this one and another small presentation on diuretics, and discuss among the friends and try to develop the valid questions which we can answer and can